Okay, so hello everyone. This, I'm afraid, is going to be a bit techier than the last talk, so I hope you enjoy it. It's going to be a very short talk. This is it. You can't hear the words. I have to do the words, and I can't do the mad doorman at the Abbey Road studio, if you can hear those, but what he actually says is there is no dark side of the moon, really. As a matter of fact, it's all dark. And that's the talk, so we can go home now and go on to the next one. There is no dark side of the moon. What there is the side of the moon, as was just beautifully demonstrated, which is away from the sun, and that is dark. But there is also the far side of the moon, and that's what's illustrated. So what there is the far side of the moon, which is shown on this diagram in green. And the moon is tidally locked to the Earth, so when you look at the moon, you always see the old man in the moon. You never see, or if you're Chinese, you see Chang'e, the princess who lives in the moon. But you never see the far side of the moon. And so the moon spins every 28 days, which is exactly the same time as it takes to go around the Earth. While we're on the Pink Floyd, there's an urban myth out there that the spectrum is the wrong way around. It's not. This is a picture of a real spectrum going through a prism, and you can see it's the same. Demolishing urban myths. Just to emphasize, therefore, the dark side of the moon is the opposite side to the sun, whereas the far side of the moon is the opposite to the Earth. And we always see the same side because the moon is tidally locked. And just to be deeply irritating here, I wish to point out that our moon is spelt with a capital M. You sometimes in the media at the minute see it spelt with a small m. This is due to a typographic error in an American manual for how to do stuff. And it has propagated deeply throughout the whole of Western society, despite the fact that everybody in the business, if you like, wants to call it moon with a capital M, including NASA. But anyway, so please use the moon. The moon is an object as opposed to a moon, which is the thing which flies around the planet. I told you that we always see the same side. The other side looks different. So this is the far side of the moon. This is what we see when we look up into the sky at night. I do love doing the moon for my work because it does mean that you can go out at night and you can actually say, oh, that's me, and there's a widget that I made is actually sitting on there, and it's good. Anyway, what you see when you look up is two colours. You see a silvery colour, this bit here, and you see a darker colour, this bit here. And in the Middle Ages, when people didn't know that much about the moon but could see it, Galileo, I can talk for ages about Galileo, and maybe if you invite me back sometime I will. In those days people thought this was a sea, and so it's called Maria. We'll talk a bit more about what that actually is, but the point is that they're only Maria on the Earth side. They're not any Maria at all on the far side. All you see is what we would now call the Anorthocetic Islands, this stuff here. So, once again, the far side is different. But they're locked together, and this is actually a double planet. The moon is our 8th continent. It's about the same surface area as Africa, if you want to look at it like that. Was it always the far side? Well, I've just showed you this picture here. which shows that all the deep impact basins, these are deep impact basins which are filled with lava, are on the side that points towards us. If you actually ask yourself, as the moon is flying through space, whether it's more likely to have things on the side pointing towards the Earth or away from the Earth, it's much more likely to have impacts on the side pointing away from the Earth. And this was pointed out by a guy called Mark Wieczorek. The other thing that you perhaps want to know is that the crust of the moon is off-centre. So it is thinner on the near side than it is on the far side. On the far side, it's about 100 kilometres thick, whereas on the near side, it's about 60 kilometres thick. In other words, the moon is lopsided, and this is the bit that's pointing towards us. So naively, before people thought about it, they thought that's why it points that way. But actually, if you do the sums, you can show that it's equally stable both ways round. And in fact, therefore, what Mark Wieczorek suggested was that in the past the moon was the other way round. And that's where most of the craters that you see were formed really early in the solar system. That's when they got formed. Comparatively late on, you had a big bang, a really enormous thing hit the moon, it flipped the moon, there's a 50-50% chance whether it comes back the same way or the opposite way, and it came back the opposite way. So now we see the impact craters. That's Mark's theory. There's a good candidate for what caused that bang. This is actually on the far side of the moon. This is the South Pole Aitken Basin. This is the biggest impact crater in the solar system. Actually, that may not strictly be true anymore. They may have found some bigger ones, but it's a great big hole, okay? You can see it goes from the South Pole here nearly to the equator. This is a contour map. So blue is low, red is high, so red is highlands. This South Pole Aitken Basin is almost planet-sized. It's almost at the level which would have split the moon up, destroyed it. So that's, and that was at the end of what we think of as the late heavy bombardment period of the moon. In other words, the period when there's still a lot of stray matter flying around the solar system. So this is something that almost made it to be a planet, but not quite, perhaps. So that's a good candidate for having done the flip. Why is it tidally locked now? The same as all other moons are tidally locked. It's because you have tides when you have the gravitational attraction between the Earth and the moon, for example, or any planet and any moon. The water on this side is more strongly attracted, so there's a bit of a bulge this way. On this side it's less strongly attracted. I'm looking at this one here. And so there's a bit of a bulge that way. So the Earth, compared to this, is slightly elliptical. You see that much clearer in water than you do in rock, but nevertheless it's also true in rock. So the moon is slightly elliptical. The difference being that it's settled down into that configuration. So the reason that we have a tidal locking is because we've reached the condition, to be technical about it, where you have the minimum transfer of angular momentum between the moon and the Earth. And that's when you have a permanent bulge here, which always points at the Earth. And this is the norm for moons. Anywhere in the solar system, nearly all the close-in moons, but most of the moons in the solar system, of which there are many, are tidally locked. Planets are also tidally locked to their stars. And did I? Yes. So I just wanted to show you this. This is an even more extreme case, which is only just discovered in the last couple of, well, no, a bit longer than that. No, I take that back. But this is a more extreme case. This is Pluto and its moon Charon. This is a genuine double planet, except that it's not a planet because it's not a planet anymore because it's too small to be a planet, which is completely correct. It is, this is, there are moons that are bigger than Pluto. It's a small thing, but it is locked to this object here. And in fact, because they're so similar in size, and the Earth and the moon orbit around a point which is inside the Earth. Pluto and Charon actually orbit around a point which is in between them because the masses are more comparable. But the point that I was making before I got sidetracked was that not only is Charon tidally locked to Pluto, so if you're sitting on the surface of Pluto, you always see the same face of Charon. Pluto is also tidally locked to Charon. So if you're sitting on the surface of Charon, and it's this surface, if you see this surface, you never see Pluto, if you live on this surface. If you live on this surface, then you always see Pluto, and you always see the same surface of Pluto. So the two halves of that double planet system are genuinely locked together. So that's tidal locking is the norm. When I was first asked to do this talk, I thought, well, there is no dark side of the moon. I can't do that. It's, you know. But as I said to Joe, once upon a time, way back in my youth, I did physics and philosophy at Oxford. That was before I discovered that I can't think precisely enough to do philosophy. And so I was sort of tickled by the idea of coming back. The other idea that tickled me was that I'm from Aberystwyth. Have I got a logo here? No, I may have gone through it. Anyway, when I started thinking about where the dark sides of the moon really are, okay, there's the bit that always points away from the sun, but there are some bits of the moon which never get illuminated at all. Conversely, there are some bits that are nearly always illuminated. So if you imagine that the sun is over here somewhere, and I'm in a mountain on the north pole of the moon, then it's always going to be in sunshine. Whereas if I'm in a deep hole at the north pole of the moon, it's always going to be in shade. And these things really happen. And a famous example is the Shackleton crater at the South Pole. So you get these permanently shadowed regions, and that really is the dark side of the moon. This is the rim of Shackleton, and this is what is sometimes called the peak of eternal light, because it's a mountain, it's a raised rim around the crater that's nearly always in sunlight. So if you want to make your lunar base, that's where you do it, because you get solar power nearly all the time. However, so that's this bit here. However, just next to it is Shackleton crater, and I think I have to do this to make it work. So this is seasonal illumination on the moon, and you can see that there is a region there which is nearly always in sunshine. It's actually this one up here, but you can see that inside the crater it's always in shade. So this is really the dark side of the moon. And it's cold in there. Right, we'll come back to that in a minute. Let me say one thing first, very briefly, but I'll harp on it again a couple of times. This iconic picture now is, in the last couple of years, it's only just been taken by the ALMA observatory, but this is a solar system forming. So this is a very young solar system, this is a star, and these tracks here have been identified by many, but not all people. But most people, I think, would say that these are planets beginning to form. So this is a new solar system on the make, and in the last 10 years we've discovered about 1,000 of these. And that's completely changed the way we look at planets, because it's now obvious that planets are all over the place. Any self-respecting star has some planets. People didn't know that before. Now they do. And so things have moved on an awful lot. I want to go back. It's 50 years since the Apollo era. And people landed on the moon. And here is someone climbing down a ramp. I had dinner with him once. And what is climbing down onto here is a dismal sandy, sort of not very interesting surface. And the astronauts brought back about half a ton of this surface, and it's been analysed and analysed and analysed very, very carefully, and indeed has pushed forward the ability of the human race to analyse small samples, which has now been used in all sorts of different ways. But the result of this enormous technical triumph was that people think they know all about the moon. We've been there, we've walked around on the surface, we've brought a load of stuff back, and for about 30 years, nothing much happened in lunar science because everybody thought that we'd done it all. First thing to remember is that they weren't interested in bringing back samples, they were interested in bringing back astronauts. And so they landed in places which were easy to get back from. Those are places near the equator, on the Earth side, and very, very flat. If you did that on the Earth, if you landed on somewhere near the equator, on the Earth's very, very flat, you would bring back half a ton of Saharan sand. And if you knew nothing at all about the Earth, that would tell you a tremendous amount about the Earth. It really would. If you think about, the universe in a grain of sand, you would get an awful lot, but you wouldn't get everything. And particularly, you wouldn't go to all the other places. And it's now clear that the places that the Apollo landers went to were not terribly average places. Almost the first thing they did with this sand regolith, to use the posh word, when they brought it home, was they looked at it for water. Up until fairly recently, before the Apollo missions or the space age, people had thought that there was water on the moon. You can see rivery sorts of things. So they looked for water, and they analysed it at the state of the art, and they looked at these bits of rock, and sure enough, there was water in there. And then someone pointed out that the isotope composition of that water was exactly the same as this was in Jet Propulsion Lab in Pasadena, and the isotope concentrations in the rock was exactly the same as the isotope concentrations in the water supply in Pasadena. So they thought, oh, we've contaminated it, and nobody thought about it again for about 40 years. These days, there are people just down the road in Milton Keynes in the Open University who can now do this experiment accurately enough to tell you that the isotope ratio is not exactly the same as Pasadena water. So what's in those rocks at quite a low level is actually genuine water, endogenous water, which has been there for the whole history of the moon. So putting these three things together, however, people had come to the conclusion that the moon was completely dead. But it is gloriously simple. This is the other great thing about the moon, is that the physics, the geology, the geochemistry, everything is much, much simpler than the Earth. There's no water much to mess things up. So if you do the plasma physics of the moon, it's dead simple. The solar corona, which when it gets to us is called the solar wind, the moon is just a lump of rock, just a lump of insulator. There's no atmosphere, no magnetic field, no nothing. Solar wind hits it, wham, straight into the surface, and you get chemical reactions on that surface. Behind it, there isn't any solar wind, and you get the most perfect vacuum in the solar system until the solar wind flows back round. The Earth, of course, we have an atmosphere which protects us from a lot of this stuff, so that this stuff is hitting the top of the atmosphere. At the moon, it just hits the surface. So you get what's called space weathering, which we'll talk about more if I can talk fast enough. The geochemistry, or the geology of the moon, is gloriously simple. There are really only three basic... so for those of you who, like me, I'm a physicist. I was once tried to be a philosopher. I have trouble when geologists and geochemists talk to me because they all use lots of words like pyroxene that I don't really understand what they mean. because like any scientific discipline, they have their own language which tells them what they need to know. So you have minerals. Minerals are assemblages of elements in particular structures. So, for example, pyroxene is a structure which has SiO3 in it, and then either calcium, magnesium, or iron. And depending on this little diagram here, which is a mixing diagram, this is iron, magnesium, or calcium, depending on which of those you've got, then if you're up this end, you're enstatite, and so on and so on. And so there are different words for all these minerals, but what you're actually saying is that those elements are in a particular structure, particular crystal structure. And then to make rock, and on the Moon, there are only 3 basic mineral groups. There's pyroxenes, there's olivines, and there's plagioclase. And that's it on the surface of the Moon. It's dead simple because the formation of the Moon was so simple, because you just had a melt of rock, and it slowly cooled, and this is what's left when you cool a melt of rock. This is what the crust that's left on the surface. So those are the 3 basic mineral types, and rocks are just mixtures of minerals, and so you mix those 3 together, pyroxene, olivine, and plagioclase, and you get rocks. So, and there are only 3 sorts of rock on the Moon, pretty much. Are there any geochemists in the audience who are going to kill me? Good. We might make it to the end of the talk. There's basalts, there's anorthosites, and there's other stuff. And I've already shown you, pretty much, again, where those things live. So, this dark stuff that you see when you look up at the night sky and see the Earth side of the Moon is basalt. And this is the youngest stuff. So this is big impact craters that have been filled with lava. That's what's going on there. That's why they're flat. It's because it's flowed up through cracks in the bottom and spread out. So this is basalt. The far side and the south of the near side, the silver bit, when you look up at the night sky, is the anorthositic feldspar, plagioclase feldspar. So this is the oldest of old rock on the Moon. This is the crust that's left over from when it first was a plasma ball, and this was what congealed on the surface. So you can see, if you look at the craters, there are far more craters here than here, because it's been around longer, and so in the history of the 4.5 billion years that it's been there, a lot more has banged into it. So this is seriously damaged, if you like, whereas this, the lava has flowed over most of that damage. So underneath that lava, you'd see stuff like that. The third group is this one, the South Polar Aitken Basin, which is different because it's actually gone deep enough that it's got towards the mantle of the Moon. So, the Moon is dead simple. You know, I've just told you all the geology and all the plasma physics in... How quickly did I manage to get through it? About 3 minutes? It makes a fantastic natural laboratory because we can actually watch simple processes going on in the space environment. A group of us at the International Space Science Institute in Bern put together a list of the 7 places on the Moon you need to go to answer 7 key questions. And this is really now more and more in the light of thinking not just about our particular moon, or indeed how you form the Earth-Moon system. And that is, by the way, not particularly clear in another talk, if you ever want another talk. But it's generally felt that a large impact at some point quite early in the solar system created an awful mess, and out of that mess, 2 different bodies congealed, the Earth and the Moon. So this is everything on the Earth has been messed up by the fact that we've got loads of running water and weather and stuff, so it's all, and you know, green things have grown over the top. But on the Moon, it's gloriously simple. So these are the 7 big questions, and the only one I'm going to have time to talk about today is volatiles on the lunar surface, and I'll talk a bit, if I have time, about Reiner Gamma. So, I talked again about the earlier epochs of the moon. It's 4.5 billion years old, as is the solar system. Nothing very much has happened on the moon for the last 4 billion years. So when the Apollo era people said it's dead, they're not that far wrong. But they're a bit wrong. So this is in half-billion-year intervals, the volcanic activity that you can trace on the surface of the moon. And so certainly there was still stuff going on 1 billion years ago. At this time it had a magnetic field, and so that did quite a lot in terms of, what's the word I'm looking for? It has cooled off since then. So there's not a lot of activity going on now. But there's still some, and indeed the latest very high-resolution images from the NASA Lunar Prospector suggest that there may even be vaguely current, 1 million years or so, it's hard to tell, volcanic activity even now. The big question, which you've, I'm sure, come across, is in the last few years, and quite a few years, not that many years, it's become clear that there is water on the moon. And this is confusing because of the way that people like me talk about it. So what I'm going to try and do is give you a very simple driving lesson about water on the moon. And the first thing to point out is that there are different sorts of water on the moon. There's the moon in the deep interior. There's the moon, there's the water in the deep interior, which was left over from when it was formed. There's the water in these black holes. Black holes is the theme for today, I think. So here's a black hole for you. Because when a water molecule gets in there, it's very, very cold, and it acts, for those of you who've used a cold trap in the lab, the water just freezes onto the surface and never leaves, and that's true for billions of years. And so you accumulate water in the bottom of these holes. Where does that water come from? Well, maybe it comes from asteroids, maybe it comes from the solar wind, maybe it's stuff that's made its way up from the interior. That's a really complicated question, which I'll try and give you in the 10 minutes that's left a driving lesson on. But the thing to understand is, so this is the different routes that water gets around the moon. The stuff that's left over from the formation can diffuse outwards, and equally stuff that's on the surface can diffuse inwards. Anything that's on the surface can get desorbed by solar wind activity or by solar ultraviolet, and will bounce around on the surface until it reaches one of these permanently shadowed regions, one of these cold traps. In addition, solar protons, in other words, the corona that we heard about earlier, has nothing to stop it hitting the surface of the moon, where it does chemistry. And 50% of the atoms on the surface of the moon are oxygen, and if we think that the speed of the solar wind is 400 kilometers a second, and it's been blowing for 4.5 billion years, and its density is about 7 protons per cc. In the history of the moon, that's an awful lot of protons that have hit the surface of the moon and basically hit oxygen atoms. So you're blasting hydrogen atoms into oxygen, and although it's not easy to do, you make water that way. And this was established by the Chandrayaan mission. This was the first Indian mission to the moon. I was responsible for the X-ray instrument on this mission. This is still my favourite launch. I just love the Indian rocket. I think you were talking about Vishnu earlier. To me, this looks just like Vishnu, you know. This is a god of destruction with his 8 arms sitting here, about to launch off and end up orbiting in space like some bad giant's head. And on the Chandrayaan spacecraft, there was an instrument provided by American colleagues. Carly Peters led it, and her colleagues at Brown University in the US. It's called M-Cubed. And this is their map of the surface of the moon. And the blue bits here, which you can recognize by their molecular signature at 3 microns in the spectra, in the infrared spectra, this is water. So there is a miasma of water on the surface of the moon at the poles. And this was a revelation. When people actually went back and looked through their data, several other people found that they'd seen it but hadn't really noticed. So now we have 2 sorts of water. We have the water in the Apollo samples, and we have the water at the poles. Yes, this is just to show you that at one stage people thought there was actually running water sometime on the moon. This is actually not running water. This is volcanic lava. But what I actually wanted to say here was that there are 3 sources of lunar material. There's solar wind material, which I just talked a bit about. There's the ancient original primordial material, and there's also deposition by comets and asteroids which have hit the moon subsequent to its formation. And as I said to you, when that happens, you form individual water atoms, or HO individual water molecules, it's not the physicist, or atoms, or OH hydroxyl radicals in the surface, and those get knocked out and they bounce around. And the height that they bounce depends on the temperature of the stuff they're bouncing off, but is typically a few hundred kilometers. These are big bounces. You know, this flea is going like crazy. But as they get towards the poles, the bounces get smaller and smaller and smaller because the surface gets colder. And when they finally reach one of these cold traps, they fall in. So if a comet hits the surface of the moon, sooner or later, all that water in the comet, comets are 50% water, is going to end up in a polar, or a large fraction of it, or an appreciable fraction, is going to end up in a polar trap. So these are north and south views of the lunar poles. This is the South Pole. There's more water at the South Pole. You can see these shadowed regions here, here, partly here, here. You can see the regions in blue where water has been seen. Same to a lesser extent at the North Pole. So that was in infrared. This is another picture in ultraviolet. And again, same idea, except that now the black is color-coded from measurements of the lunar surface. So what these people are seeing in ultraviolet is which ultraviolet detects water that's really close to the surface. So what they're saying is that in some, but not all of these craters, and the colder they are, the blacker they are, but in some of the coldest ones, you've got a deposit there of water on the surface. There's another one. Just to confuse things, here's another one. This is now taken in a different technique again. This is done in radar, and here you see a signature which looks like water from some of these craters, but not others. You also see young craters which have the same signature, and you also see bits of permanently shadowed. You see permanently shadowed craters, but sometimes not the whole of the crater is permanently shadowed because of the configuration of the mountains around the side. And so you get partly shadowed, and in some of these ones the water is in the wrong place. This is another way of looking at it. This is epithermal neutrons, courtesy of Dave Lawrence, and this is, so again, what you've got here is some craters have got a lot, some craters have got much less. So it's really variable, and there isn't a coherent story on the moon for what's actually going on. Is there ice on the surface? Is there dew on the surface? Has it got mixed in to a depth of 10 meters, which is what the gamma ray measurements would say? there's something going on there, but it's not exactly clear what. I just got back from Kourou, where we launched the Bepi-Colombo mission to Mercury. Mercury is like, if the Moon is planets 101, Mercury is planets 201. It's just a bit more complicated. But at Mercury, it's very, very clear that you have got water ice trapped in the permanently shadowed regions. It's much clearer at Mercury, for some strange reason, than it is at Earth. Mercury also is tidally locked, by the way, but to the Sun, not the Earth. So the third way, which I already so that was comets. The third way, which I already described to you, was protons hitting the surface. And I said that there was no magnetic field on the Moon. There are, however, magnetic anomalies. And this is a map of the magnetic anomalies on the Moon. Again, a whole interesting story which I haven't got time to go into. But these anomalies create mini magnetospheres, just very localized magnetospheres. And so those will exclude the solar wind from just this limited geographical region here. This is a diagram by Ruth Bamford from just down the road. And underneath these mini magnetospheres on the surface, this is what you see. You see these swirls of, and again, we're talking about the light side of the Moon and the dark side of the Moon. This is actually a mixture of bits of light and bits of dark. And the difference is that solar wind has hit some of these and not others. All swirls are associated with magnetic anomalies. The bright swirl regions have weaker water absorption, which implies that the hydrogen is depleted by solar wind activity in the bright regions, but not in the dark regions. So this is actually a laboratory for making water on a bare, airless planet. This is how it's done in the universe. There's an even more extreme version, which is highly controversial, and I'm not certain that I want to recommend it to you, but recently these guys, Voller et al., have actually suggested that they can see dew on the surface. In other words, they see that the amount of water goes down, this is the green line here, at noon, but is higher at dawn and dusk. So that's really controversial. And the way to tell is that you look at the isotope ratios. So what we badly need to do is fly a mission to the Moon which can measure the isotope ratios. So in conclusion, the Moon is by far the most accessible space laboratory we've got for understanding processes at terrestrial planets in particular. In a simple environment, we can get to the Moon, we can fly experiments to the Moon, and we can work out how you do planetary formation and planetary chronology. There's an enormous amount that needs to be done in terms of understanding the dating of the early solar system. It's very simple, which makes it easy to easy. Oh, a lifetime's work, but you know what I mean. It's conceptually easier to understand what's going on, but what it shows is an amazing complexity. So, thanks.
Thank you. Great. Well, thank you, Professor Grande, for an illuminating talk. I'm still playing Pink Floyd in my head from the beginning. I apologize.
I can put it back on if you want.
We don't need no education, right? So let's
well, that puts us out of a job, doesn't it?
Right. Let's have some questions from the audience, please. And there's one up there.
It seems extremely significant that the mare, or the volcanic action, is on the surface pointing to the Earth. Is it the Earth that has affected the volcanic action?
No, as I said, it's quite possible that that when those regions actually formed, they were pointing the other way, because you're less protected that way. And in fact, the motion of the Moon means you're more likely to hit big things if you're on the far side of the Moon. But chronologically, we're talking about 4.5 billion years. most of that activity, or that cratering happened in the first 400 million years of that time, pretty much. Those big craters were all older than 4 billion years. So that was what made the holes which the lava then seeps into. So it may be significant, but it's probably not anything to do with, well, in a roundabout way. Do you see what I mean?
Thank you. Over on the left here, please.
Oh yes. If you could put a moon base anywhere on the moon right now, where would you put it?
You'd put it... the latest data seems to suggest that there isn't much water at Shackleton, which makes it a bit more difficult, but what people classically always say is Shackleton, because you have the solar panels there, you know, the solar power availability there. And if you've got water there, then you can, you know, you've got a lot of what you need. The real thing with lunar bases is that you need to be able to survive the night time. Remember that you've got a 14-day night time. And so that's the real, so that's why you, first off, you wouldn't really want to put a moon base near the equator, although it's much easier to get back to Earth. If you've got people there, then you have to keep them warm.
Thank you. On this side, please.
Right here, thank you. I have two questions for you. The first one is, we know that NASA has just launched, is back to the moon mission recently, and the Chinese are trying to build an artificial moon in the space, which is kind of really like essentially a huge mirror in the space. What do you think about that? And the second question is, there's a group of research fellows from Stanford University that just discovered an alien spacecraft has just passed through the solar system. So what do you think of that? Thank you.
Oh, the second one first. I actually, earlier this year, convened a conference in Lausanne on what science we should be doing in 2061. 2061 is the next time that Halley's Comet comes back around. But one of the most popular things was the alien spacecraft. Now, I mean, as you know, I'm sure that the spectrum of it is not, you know, shiny metal or anything like that. It's actually pretty much the same as the moon. It's rock. It's magnesium, silicon, and aluminium. So it's a big shard-shaped lump of rock, but nevertheless it is extrasolar and travelling at high speed. And so the question is, 2061, would you have the technical capability to go and rendezvous with one of those things? And if you actually look at the statistics of occurrence, it's likely that one of those actually comes through the solar system every year. It's just that we haven't seen it before and haven't been looking. On the first talk, if you ask me who are the people who are going to, so the first question, who's going to bring samples back from the moon next? That's going to be the Chinese. It's Chang'e, I lose track of the numbers, Chang'e 3 in, which is, I think, next year supposed to bring a lunar sample back. So the Chinese space agencies have really leapfrogged NASA doing that. Equally people. I bet you that there's a Chinese person on the moon before there's the next American.
Question here, please.
There's three quick ones, if I may. First of all, I take it that since you're describing it as a double planet, the suggestion at one time that the moon had been displaced by a big bit being knocked off the Earth is unlikely.
No, I think that is likely. Thea, as it's sometimes called. Yeah, no, but this was very early in the solar system.
Right.
So, yeah, the idea was that Thea was Mars-size and hits a very grazing incidence blow on the surface. There are a lot of problems with that. When people first came up with that idea, they looked at the isotope ratios of the mantle and the moon and thought they were very similar. The more time, and therefore that most of the moon was made of the mantle of the Earth, the more sophisticated those measurements have got, it's now very clear that if it was true, then most of the moon is made out of the remains of Thea. But it's still the best theory.
The second question, if the Earth were not full of seas, would it have tidally locked to the moon as well?
I don't think so.
Because it would be a rock structure that would then form...
You mean it would be
elliptical
permanent? I think the rock would lock anyway, wouldn't it? But I think basically they're too far apart.
Okay.
And the third question, you talked about the impact craters. Is it not possible that the stray matter was attracted by the double planet and a proportion of it went past the Earth and therefore hit the near side, rather than having a flip?
Witzerer did, I think, quite a careful statistical analysis of how likely it was, and he came up with a 1/3% likelihood that it was the way round that it is now. But I think he did put things like that in.
So on Earth, most sand is created by water eroding rocks and mountains. Where does the dust and sand on the moon come from?
4.6 billion years of impact. Basically, the surface has been pulverized over a very long period of time.
I'm sorry, Mr.
Just a quick comment on that. The angular momentum between the Earth and the Moon is constant, and the Moon is going away from us. In fact, we are lucky to see solar eclipses today, because in a few million years, or hundreds of millions of years, the Moon will be smaller, so it will fail to cover the entire Sun. So it's going away, stealing angular momentum from the spin of the Earth. So the Earth day is getting longer, a fraction of a second every century, and that can be measured very accurately. So in the far future, thousands of millions of years to come, the Earth and the Moon will be gravitationally locked. So the Earth will stop, and the day on the Earth will be as long as a month, as a lunar month. But by then, the solar system will have been destroyed already, because that will be before the death of the Sun. Yeah. And on the heavy bombardment, is not only the Moon and the Earth. The heavy bombardment happening in all the inner part of the solar system, Mercury and Venus and Mars and all of them. And I doubt that the gravity of the Moon and the Earth will be enough to deflect any asteroids incoming, because they come very fast and they just go straight. They don't see the gravity, I think.
Okay, thank you. Thank you very much. Please join me in thanking Professor Grande one more time.